These are the chi-square testing notes 3. Today we're going to talk about the chi-square test for homogeneity. And we talked the other day about there being 3 types of chi-square tests. The first type that we talked about, and that we've talked about the last couple of days, starts with a G that's called the goodness of fit test. And we specifically use this type of chi-square test if we're comparing proportions for one characteristic of one population. And data is contained on a one-way table, which means that you have one set of numbers that you would put into like one var stats, and it makes up one row or one column. An example might be flavors of Trix from a box. We did a Skittles example yesterday where everything was in one row. The test we're going to look at today starts with an H. It's called test for homogeneity. And the difference here is that a test for homogeneity compares proportions for 2 or more populations instead of one population like we had yesterday. You'll also see that our data is going to be contained on a two-way table where there are multiple rows and columns of data. The third type of test, which we'll talk about in a couple days, is a test for independence. And that will compare proportions for one population, but also uses information on a two-way table. Our focus today, though, is on the test for homogeneity, and I want to take a look at the different parts that make up your significance test for this type of chi-square test. The hypotheses for this type of test usually we don't use symbols for. It's going to be kind of a blanket statement. The null hypothesis is going to be something like the blank proportions are the same for all blank. For the alternative hypothesis, I'm going to cross off the word same here. And we're going to change this to are not the same for all. You could also use the phrase different. The blanks describe the rows and columns of the two-way table. More on this in just a moment. The first condition for a test for homogeneity is that independent random samples are taken from the population because, again, we're working with 2 or more populations. So similar to the 2-sample t-test, the 2-proportion z-test, we're looking at independent random samples. We're going to have a table of expected values, and to calculate each expected value, we're going to use a formula that you can see right here. More on this in a little bit. Once we make the table, again, we're going to check that all expected counts are at least 1 and 20% or less if all expected counts are less than 5. When we carry out the procedure, it's the same formula for calculating chi-square, but this time the degrees of freedom are a little different. To find the degrees of freedom, we take the number of rows in the table minus 1 times the number of columns in the table minus 1. Now here's a little word on how you calculate the expected values. I want to take a look at an example where maybe we have 2 classes. We'll call this first hour and third hour. And our first hour class can be divided into boys and girls, as can our third hour class. So let's say we use these values. Let's say that there are 16 girls in first hour and 14 boys. And then third hour, we're going to say that there's 12 girls and 28 boys. To calculate the expected counts, what we do is we take the row total times the column total divided by the table total. So what we're going to do in our observed counts is that I'm going to calculate the row and column totals. For example, the number of girls when you add 16 and 12 gives you 28. We'll put 28 on the outside here. And we'll calculate the totals for these other rows and columns as well. To calculate the expected counts, we're going to use the same headings that we did before. So we'll have girls and boys in these 2 row headings, and first hour and third hour as our column headings. The expected counts are going to make sure that what we get for values are proportional compared to what we have, which might not be proportional. So here's what we do. To calculate the number of girls we would expect to see in first hour, we're going to take the row total for girls, which is 28, multiplied by the column total for first hour girls, which is 30. And we're going to divide this by the table total, how many people there are altogether. So if you add 30 and 40 or 28 and 42, that gives you 70. So we're going to take 28 times 30 and we're going to divide this by 70. This will give you the expected counts. And then we're going to do this for each value in the table. So for boys in first hour, the row total for boys is 42. The column total is again 30, and then the table total is always going to be out of 70 in this case. And we're going to calculate this out for every cell in our table. So for girls in third hour, the row total is 28, the column total is 40. We do 28 times 40 divided by 70. And then for boys in third hour, the rows total in this row here is 42. The column total is 40. And we're going to divide that by the table total, which is 70. So now we're going to get our calculator out. We're going to calculate what each of these values in these cells are equal to. So when we do 28 times 30 divided by 70, we get 12. I'm also going to take care of 28 times 40 divided by 70 on the top row, and that gives us 16. Now, what's kind of cool is this. If you realize that the first value here is 12, and that this row has to add up to 18, really you don't have to do the calculations for this next number because you know that 12 plus whatever this value is equals 28. In a similar manner, because you know that this row or this column here adds up to 40, you don't really have to do the calculations here if you know 16 plus what equals 40. Now, if you aren't sure, you could always calculate it here, but you should get 24 because 16 plus 24 equals 40. And likewise, if you realize that this row adds up to 42 or that this column adds up to 30, the missing blank that should go here is going to have to be 18 because when you add 12 and 18, you get 30, or when you add 18 and 24, you get 42. A quick calculation will verify that that is the right value. Now, how else do you know that these are the expected counts? Well, I mentioned that you should end up with proportional values if these are the expected counts. And what we mean by that is if you're to take the girls' totals for first hour and third hour, if you're to take the 12 and 16 and divide them, you're going to get 0.75. If you take the boys' totals for those 2 hours as well and divide 18 by 24, you should get the same proportion, 75%. It also works vertically. If you take the proportion of boys to girls or girls to boys first hour, which is 12 to 18, that's a 2/3 ratio. And if you take 16 over 24, the two numbers in that third hour column, and divide them, you get the same thing. So the expected counts that you end up with will always be proportional to each other. One last thing I want to point out, if we go back to the top of the page here, with our hypotheses, if you're dealing with our null and alternative hypothesis in this setting, what you could think about here is that the genders are the different proportions we're working with. So if you wanted to say like the gender proportions are the same for all, now the different populations we're working with are hours, first and third hour. So if you want to say like the gender populations are the same for all hours, the gender populations are not the same for all hours, that's how you would kind of set up your hypotheses here. So now let's actually try out a test and see if you can put all these different parts together here. From the 2002 AP exam, a survey was given to a random sample of students at a university. Include a question about which of two well-known comedy shows, S or F, students preferred. Students were asked the question, do you prefer S or F? And the responses are shown below. Now we're going to bypass part A and part B, and we're going to move right on to part C. In a follow-up survey, a separate group of randomly selected students was asked, do you prefer F or S? Notice the order has changed. In the first question, we said, do you prefer S or F? Now we're asking, do you prefer F or S to a different group of students? The responses are shown below. Based on these two surveys, is there evidence that the stated preference depends on the order in which the comedy shows were listed in the survey question? Justify your answer. Well, we have two different samples we're taking here. You could almost imagine you could put these two charts together and you'd have kind of a two-way table. So you've got our S's and our F's. We have our totals for both of our rows here. It's a two-way table, plus we have two separate populations that we've gathered our data from. So this indicates that we would be working with a chi-square test for homogeneity. So what would your hypotheses look like here? Well, you could talk about proportions. For example, you could say the response proportions are the same for both groups. It gets a little wordy. Remember that you can always use the question itself to help you set up the hypotheses as well. So if they say, is there evidence the stated preference depends on the order in which the comedy shows were listed? If there's no difference in the null hypothesis, what we say is the stated preference does not depend on the order. And your alternative hypothesis is there is a difference. The stated preference does depend on the order. We next name our procedure. This is called a chi-square test for homogeneity. You probably remember that for this type of test, we do not need to say anything about parameters or populations. Our next step, we're going to talk about our conditions. The first condition is independent random samples were taken. And they do mention at the beginning of the problem, we do have a random sample of students at the beginning. And in a separate follow-up survey, a separate group of randomly selected students were chosen here. So if it's a separate group, that infers independence. So independent random samples were taken. Now the next thing we do is we make our expected counts table. So similar to the one that we have kind of existing in our problem, I'm going to label this expected counts or expected values. I'll call this first row kind of like the first group of people we surveyed, and then the second group of people we surveyed. And then S will be the number of people that chose Seinfeld, and the other F for friends. And what we'll do, similar to what we did on the front side of the worksheet, is we'll calculate our expected values by multiplying row totals times column totals and dividing them by table totals. So if we go up to the top of our page here again, if you add the 185 and the 68 together, you're going to get 253 that preferred S. If you add the 139 and the 88 together, you're going to get 227. And if you add these two totals, or if you add the 324 and 156, you should get 480. So when we calculate our expected counts, we're going to take our row total. So if we're taking kind of this value that's in the upper left corner here, like this 185, we're going to take the row total, which is 324, times the column total, which is this 253, and we're going to divide it by the table total, which is 480. And when you do that, you get 170.775. You do not want to round this value. Even if it's a long, ugly decimal, we're going to write it out as seen here. I'm going to calculate one more value for you, then you can calculate the other two. To find the value that would correspond with this value right here, the row total is 324, the column total is 227, and we're going to divide that by the table total of 480. And when you crunch out these values, what you get is 153.225. If you would like to calculate the other values, you can go ahead and do so, and we will take a look at what you get here in just a moment. So in multiplying the row totals times the column totals divided by the table totals, you'll see the two numbers on the calculator right here that we got, and I've added those values to our expected values chart. Now, because all these values are not only bigger than 1, but they're also bigger than 5, you can actually combine the two conditions that we talked about here. Yes, they're all bigger than 1. If they're bigger than 5, then they're automatically bigger than 1. So I'm just going to make a note here that all the expected values are greater than 5. And if they are, that's the only sentence you need to say here. You don't have to say they're all greater than 1 and none of them are smaller than 5. You can just say this. And now we can move into calculating what chi-square is equal to. To calculate chi-square, what we do is we take each observed value. For example, in the top left corner of our chart here, we had that 185, kind of from our first survey group that preferred S. So we're going to take 185, we're going to subtract it from the 170.775. We're going to square it, and we're going to divide it by 170.775. And we're going to do this, that's not very good, we're going to do this for each value in your table. So I'm going to show you the next one here, the 139. We're going to do that 139 minus the 153.229 or 225. We're going to square that, and we're going to divide it by 153.225. And we'll do this for the other values as well. So this is what your fraction should look like once you crunch them all up. Now if you actually type this in your calculator, we'll get what chi-square is equal to. When you type this in your calculator, you get a chi-square value of 7.709 approximately. Now remember, now when we calculate your degrees of freedom, it's equal to the rows minus 1 in your table minus the number of columns in your table minus 1. And since each row and each column has 2 entries in it, we're just going to go 2 minus 1 times 2 minus 1, which is 1 times 1, which equals 1. That's your degrees of freedom. And then you may remember to calculate your p-value. What we're going to do is we're going to go to second vars on your calculator. We're going to go to chi-square CDF. And what we're going to type in are your chi-square value, which was 7.709. A big number, usually like 999 or something like that, comma 1 for your degrees of freedom. When we hit enter, you'll get your p-value, which appears to be about 0.0055. There's not a lot of space remaining, so let's scroll up and kind of wrap it up over here. Our p-value, which we do want to state, was equal to 0.0055 approximately. And since the p-value is less than 0.05, we reject the null hypothesis. There is significant evidence that the stated preference does depend on the order. And now you know how to set up a chi-square test for homogeneity.